Hello and welcome to Fastener Connect. It is my pleasure to introduce the next presentation. But before I do, please note that a recording of the presentation will be available to view on demand. But now I will hand over to Mason Paul of Würth Additive Group and Rod Chaffee of Markforged, who will be presenting the complementary technologies of Fastener and Additive. Over to you, Mason and Rod.
Hello, everyone. Thank you for attending our webinar. My name is Rod Chaffee. I am a strategic sales manager with Markforged. And joining me today is Mason Paul. He is a sales engineer with the Würth Additive Group. And we're going to spend a little bit of time talking to you today about the complementary technologies of fasteners and additive. So Mason, if we can go to the next slide.
Sure thing.
So our agenda for today's webinar is Mason's going to take a little bit of time and introduce you to Würth and the Würth Additive Group. And then he's also going to go into a little bit of just a basic background and understanding of additive manufacturing so that everyone in the audience can have an understanding of what additive manufacturing actually is and what sort of entails. I'll share some information about Markforged and who we are as a company and what we do. And then we'll get into the meat of our presentation and talk about fasteners complementing additive technologies and how we can use fasteners to strengthen three-dimensional parts, and then we'll talk about how additive technologies can complement fasteners and certain things that additive technologies can bring to the fastener world. So Mason, why don't you go ahead and talk to us about Würth?
Sure thing. So Würth as a whole is a supply chain management company. Essentially, we will help out with supplying anything from fasteners to PPE, paint, any manufacturing goods. And so with us being a supply chain management company, we take pride in helping people avoid line downs, helping people stay stocked and have what they need when they need it. So we are a global company. We are located pretty much in every continent at this point, I do believe. And across the US, we have many locations, and you can see we have many 3D sales engineers located by the black dots, and that is quickly expanding within the Würth Additive Group. And so when it comes to the Würth Additive Group as a whole, we are essentially the 3D printing division of the whole Würth Group. And so what we like to do is we try to take our existing customers that are using manufacturing supply chain management tools and integrating additive manufacturing into that to help streamline and help them through their day-to-day tasks. So from there, the Würth Additive Group, we do tool sales and rentals. So that includes whether it be printers, finishing machines. We offer technical assistance with engineering, educational workshops, and different financial plans when it comes to helping implement these in the best way possible. And so to give a little background when it comes to additive manufacturing, it's a little bit different than traditional manufacturing, especially seen from the fastener manufacturing point of view. So fastener manufacturing is mainly produced through cold forging and hot forging, or cold rolling and hot forging. And so that is more on the formative side. So that is taking a set cast and pressing material into it, whether that be molten metal, molten plastic, and having a part come out of that from these mold cavities. Similarly with cold rolling, where you have the dies and the presses and just going through pumping out fasteners. When it comes to subtractive manufacturing, that is where you start with a block similar to a CNC, and you will mill away the actual material that is seen on there and leaving you with one part. And so additive manufacturing is kind of a combination of the two, but the goal is to have a more adaptive outlook on it. So you wouldn't need the tool setup where it comes to cavities, and you wouldn't have the waste that would be seen with subtractive manufacturing. The way that I like to describe, actually in particular, this one type of 3D printing or additive manufacturing called FFF or FDM for fused deposition modeling or fused filament fabrication. It's essentially like the way that I like to say it is like a hot glue gun or a high-tech hot glue gun. So it is extruding plastic through a hot end in a precise manner where it's being laid down in the pattern that you had designed, uploaded in the STL file. And there are other types of additive manufacturing, such as powder bed fusion, where it uses lasers to actually melt and sinter a bed of powdered metal or plastic. And there are other ones that bring in resins with UV curing. So those are just a very light overview of it.
Quick comment on that. If you can go back there, Mason, a quick comment around that. Similar to subtractive manufacturing or formative manufacturing, the technology of additive manufacturing is highly dependent on what the end use application is of the product that's being manufactured. In a traditional manufacturing world, some parts are machined and other parts are cast, primarily depending on how that part is used in the end application or the intended use of that part. It's exactly the same with additive manufacturing. Technologies are driven really towards the end use product, what you want to do with that part, how many of them you want to manufacture, how quickly you need to manufacture those. The same sort of decision making takes place within additive manufacturing as it does with traditional manufacturing on which technology best fits for what you want to accomplish. So I just want to sort of make a comment around that. To help people understand the different why are there so many different technologies, and can't we just have one? It's the world's made up of lots of different things, and we need different technologies for best fits.
And that's actually a great point. That's something that I talk to people a lot about when it comes to looking at what you can 3D print and what you should 3D print, because obviously there are certain manufacturing methods that are in place and they've been working for as long as they have been for a specific reason. So for instance, when it comes to producing high runs of fasteners, so say you're making a 1/4-20 screw, I always tell people you're not going to be 3D printing the screw that you're going to be putting in your car, putting in your tractor, putting in the office chair, things like that. But there's manufacturing methods in place where it's, if they work, you don't mess with them. But then there are other ways that technologies like this can definitely help out in a sense.
Exactly. Okay.
And actually, like I was just saying, there's a time and a place for 3D printing, and those are the low volume, high cost parts. So those are the ones where it is that you have a long lead time, it costs a lot to make of them, and you only have to order a handful. So you're not looking to 3D print something where you need to have 30 million of them every year to ship out to your customers. This is those onesie twosie things where it's not as common for you to be replenishing them in large quantities.
This is a great slide where it shows, right, of all of the components or pieces and parts that a manufacturing facility may use. Those are generally bell curve distributed, where you have some parts that you use many of them. And it's those parts aren't changed often. Fasteners lie within the really high part of this bell curve. And traditional manufacturing works well for those types of products. They don't change very often, and you need a lot of them. Oftentimes, manufacturers struggle with the tails of that bell curve, right? The blue parts, where parts are changing a lot, or you just don't need very many of them. So minimum buys become an issue. The cost of the part, because you only need 4 or 5 of them, become an issue. And this is where additive manufacturing really sort of comes into play, as is high mix, low volume parts. Instead of carrying inventory of many parts that may last you for many years, or buying items that all of a sudden the design change, so those parts are no longer useful for you. You can use additive manufacturing to print those parts on demand, which makes you much more flexible as a manufacturer, and it really helps with cost of parts, inventory management, those types of situations.
Very well put.
Okay, perfect. All right, well, let's talk a little bit about Markforged. So Markforged obviously is in the additive manufacturing space. We are reinventing manufacturing today so that you can build anything that you can imagine tomorrow. And we do that with what we refer to as the digital forge. So if you can move forward a slide, Mason, appreciate it. Markforged is the creator and the supplier of the digital forged. And the digital forge consists of 3 different parts. Obviously, the 3D printers that we develop, manufacture, and provide to the marketplace. Mason has one in his background. But along with that, the software that we use to bring in the CAD model, the part that's going to be printed, to slice that part, to get that part ready to be printed in a manner that it delivers the attributes that the end user needs of that part. So orientation of the print, composite reinforcement, continuous fiber reinforcement of that part. If it's a metal part, there could be supports that are in it, or the way that the part is printed. The software is very critical. Within Markforged, we use a cloud-based software so that it's available to our customers anywhere they can get internet access. Their parts are always available to them. It's a unique approach that Markforged uses, and our customers are always using the latest and greatest software available because it is a cloud-based solution. Our printers are also cloud connected, so from anywhere in the world and our software, you can trigger parts to print. So you can imagine if you're a manufacturer with multiple facilities within a region or around the world, you can trigger and initiate prints from any location in the world to any of your printers anywhere in the world. So it allows management of parts and part inventory from a single location, but then actually creating that part lots of places all around the world. And the third part of the digital forge is really around the materials that we offer. So Markforged offers composite printers. So it's printing an onyx material along with continuous fiber reinforcements, which allows us to print a composite part that has the strength characteristics similar to aluminum. But then we also print metal parts. So we have a metal printing system, and within metal, we can print stainless steel, we can print copper, we can print Inconel, and we can print a variety of tool steels. So we have lots of flexibility within the digital forge to the manufacturing marketplace, depending on what type of parts that they're after and what materials they would like those parts to be made of. And most importantly, what is the end use or end application of that part? And then we can help determine which is the best material and the best way to produce that part using an additive manufacturing platform, the digital forged. So the next slide sort of talks about a whole lot of applications that Markforged gets involved in. So due to the strength of our parts and the flexibility of the digital forge, we do a lot of work within tooling, fixturing, gauges, helping manufacturers manufacture more efficiently and become much more flexible in the products that they make. You read through this list, and you'll notice that fasteners are not on this list. One of the things that Markforged is very clear about is printing fasteners is probably not a really good application for the digital forge in our world today. As technology gets better and changes, is printing fasteners in the future a potential? Absolutely. But right now, it's not the right solution. You're much better off to buy those fasteners off the shelf from somebody like Würth. So instead of talking about additive being a sort of a competitive manufacturing process, Mason and I are going to talk about how additive and fasteners can be complementary of each other. How does fasteners complement additive technologies? And Mason has a couple of slides and some examples on how this works. So why don't you go ahead?
Sure thing. So when it comes to integrating 3D printing or additive manufacturing and fasteners, there's a couple different ways you can go about it. You can go through different things like heat set inserts, embedded fasteners, self-tapping screws, or press bearings. And so these are just some of the more common ones that we see. And honestly, the most impressive one and kind of the most frequently used one that I see is heat set inserts, because that allows you to uphold thread specs and uphold different material characteristics within threads on a plastic printed part. And when I say plastic, I also mean composites in the carbon fiber realm, the nylon realm, the Kevlar realm, things like that. And you're able to actually have these strong metal threads in a variety of different materials in your composite parts. And so I see.
So quick question around that, Mason. So basically, what you're looking at there is, instead of actually printing threads in your part, you're printing a hole or a void in your part that you're then inserting a threaded insert into that hole. Is that correct? Can you explain? Can you clarify that for us?
Yep. So exactly. So when it comes to getting those heat set inserts in there, it's one of these things that we call design for additive manufacturing. And so you take into account, like, this is how we used to make it, and this is how we're going to make it now. So what you would do is you would have the hole spec'd out for that specific heat set insert, and you would just essentially use a soldering iron or a heating element and have that pressed in there instead of printing the threads. Since printing threads is doable to an extent, when it comes to getting truly strong and metal threads, especially in a composite part, the best way to go through it is heat set inserts just like this. It really allows like a strong bond. As you can see, there's kind of teeth marks and almost like serrations on the actual insert itself, and that actually melts into the plastic within that hole on the part and becomes one with the part.
Yeah, interesting. So what are other ways to get threads into a part?
So another way to get threads into a part is embedded nuts or embedded fasteners in general. So down here, you can actually see, I'm not sure if my mouse is showing up on here.
Yeah, I can
right
see
here. So down here, you can actually see an embedded bolt within one of these parts. So this is a part where we had programmed a pause into the machine, and we were able to place a bolt inside of it and have those threads exposed. So that will give us metal threads on the exterior, and it'll allow us to thread it together with the rest of the assembly that it's mating with, and not have to worry about the plastic threads. So with the head of the socket head cap screw, or the hex bolt in this case, with that being encapsulated, you essentially just made a hybrid part between composites and spec'd out.
So basically, as you print the layers of your part, you tell the printer to pause or stop, and then you place a nut or a bolt or whatever your threaded component is into the part that you're printing, and then you tell the printer, okay, continue, and then it just continues to print its layers. So when the part is finished, internally to the part, without any assembly or taking apart and putting back together, your fastener is part of the component that you printed.
Exactly. And it makes it one with it inside, where it's not like it's how could I put this? It's
there's no extra step. It's essentially a composite part that's got one of the pieces that make up the composite is the fastener buried into the part.
Exactly, and it is truly
Fantastic.
embedded. It is printed in with the part, where its surroundings encapsulate it, and it's in there. It's part of the part. And actually, I've actually seen customers use magnets as a similar similar embedded part, where they use them as similar guide tools if they need their composite part to have magnetic properties further on down the line.
Fantastic.
And so going on to the last two here, self-tapping screws, it's a very similar principle to just normal self-tapping screws into plastic housings or plastic parts. And as well as with press bearings, you are able to design a part and have it printed so that afterwards a bearing can be pressed into it, to avoid having metal on metal contact with rollers, or metal on plastic, or plastic on plastic. This will give you a nice greased up ball bearing to have your wear points kind of, I guess, saved from extra wear and tear.
Perfect.
And so moving on, there are a couple different ways that we can actually use fasteners to help strengthen 3D printed parts. So inherently, when it comes to 3D printing, the weak direction, or I guess like the Achilles tendon have you, is the layer lines. And the layer lines are usually in the Z-axis, especially on the Markforged machines. The Z-axis is the direction that it prints in. And that is inherently where we do see the weakest direction for tensile strength. And so from there, what we've done in the past is we have designed through holes and have been able to set up bolts and a bolt and nut fixture to actually go through and apply a clamp load to help, I guess, assist in the Z-axis forces that the part itself might be experiencing.
Yeah. So basically, if you print a part as the layers are created, once the part is finished, the part will have the tendency to peel itself apart if there's a direction in which the part is going to fail. So if by using fasteners to actually hold those layers together, it adds strength to that direction of the part. Right? Is that right?
Correct. Yes. So it's almost like if you were to print a chain link that looked like this. If you were to print it standing up, all of the Z-axis layer lines would be running across like this. And if you were to put it in tension, you would be pulling in the same direction as it was printed. And you would see a lot less impressive tensile strength tests. Whereas if you printed it like this with the lines like this, and then you turned it and you pulled it in this direction, given you have concentric printing going on here, you are going to see a much better result in your testing. Yeah. Whereas if you print it like this, I would suggest putting some through bolts like this to help hold it all together.
Yeah, and some real world examples where I've seen things, where I've seen this used is dies for tube bending. So a tube bending die will get force in it multiple directions because it's rotating the tube as it bends. So what we've seen is those dies printed and then bolted in the Z-axis so that as the in use, as the dies rotated, or the parts rotated through the die, the bolts hold it together and there's not a separation. It adds strength to that die and it allows it to be used many more times than if it was just if it didn't have that additional strength in the part.
Exactly. And then one more thing that we would be able to help strengthen these would be tapping the holes instead of necessarily using a self drilling or self tapping screw. This will help with, I guess, stress dispersion, where you won't necessarily be pushing out all in one direction. This will help give the threads or give the bolt something to latch onto instead of necessarily just cutting straight into it. But we can actually go into a little bit more on printing threads. So printing threads is doable. It's something we do pretty often, especially with metal printed parts. However, there are limitations that we do run into. So there are different sizes, different orientations that work best for just straight up printing them off, getting them right off the printer. You're able to do things as small as an M3 and then things as large as an M10. And all depending on how you position them, regardless, you would still be able to get a threaded hole, because say that you have a tricky orientation, say that you're not able to necessarily print in one of these recommended directions, and you have to do a super small hole, a super small hole in the horizontal direction. What you're always able to do is you're always able to oversize the hole, and then ensuring that the wall thickness is proper, you're actually able to go through with a tapping set and get those threads exactly how you want them. So you don't ever have to worry about support removal, or are my threads going to come out properly if you're going to be working outside of these margins. It's something that we utilize pretty often, especially in metal thread.
Yeah, and this page is part of Markforged design guide for metal parts. So Markforged provides the market some design for additive manufacturing guides, one for metal and as well as one for composite, to help give the marketplace an idea on, you know, what have we learned that really works well with additive manufacturing, and what have we learned where you should use traditional fasteners or traditional pieces and components to help support the additive manufacturing and the part that you're making. So basically, the summary of this page really is, if it's a small threaded hole or a small, you need small threads, you're better off to tap it. Or if, as your size gets larger, then just based on the resolution of the printers, that you can actually print those threads and they'll be successful.
Exactly.
I think we have one more. Yeah, we have another slide that talks about, this is from our composites design guide. So it gives you an idea on how we approach fasteners with our composite parts. So Mason, you can go ahead and walk us through this slide.
Sure thing. So yeah, this is the first topic on here, the threads and inserts. That's something we had covered earlier on. We're talking about the composites using heat set inserts to actually get spec'd out metal threads into your parts to give better securing and better mating amongst the assembly. But also we see a lot of guide pins being used as a wear point to help disperse and kind of help give a little bit more longevity to the composite parts that you're actually printing. So in this instance right here on the, let's see if my mouse will cooperate here. These dowel pins were put in place since right along this surface right here, you were going to be getting a lot of friction. You're going to be getting a lot of wear and tear. And so if you just had solely the composite part, it would hold up well, but it wouldn't hold up for as long as it possibly could if you relieved some of those stresses and some of that friction and disperse it onto something like steel dowel pins or another surface that would take better to friction like that.
Yeah, but the example would be if you had a cast part that had a rough surface finish, and this is a clamping fixture, a holding fixture that's continuously grabbing a hold of a cast part and moving it. A composite part would eventually wear down just because of the abrasiveness of the cast part, almost like sandpaper. Every time you grab it, it's going to sand a little bit away. If we design pins into that part, the pin surface actually touches the cast part, which eliminates that friction surface on the composite part. So your clamping tool will have much longer life because those pins are going to wear versus the composite part that you printed. Right?
Exactly. And similarly with pins, you can also use them for alignment tools. This is very simply put. It's like assembling furniture. You have the dowel pins to help to make sure that all your bolt holes are lining up. Everything is in the correct spots, and even helping with securing in different directions so that you have a whole lot less part movement within an assembly. So that one is fairly straightforward. And so with that, I will move on to how additive technologies actually complement fasteners. And so first and foremost, like Rod had mentioned before, you do not suggest printing screws for use or hardware for use in that manner. They won't be able to be held to any ASTM or ASME specs. And so with that being said, really the only point, and as you can see right down here, the only point that we say that it's okay to 3D print fasteners is for form and fit tests of prototypes. So this is a common one that we see where an engineer has designed up a specific, a new type of fastener where it has a funky thread pitch, or it has a new type of drive on it. And they want to actually see it before they start to create the dies, before they start to go further into actually investing into the equipment that they're going to be using to actually manufacture it. This will actually produce the fastener so you can look at it and say, yes, this is exactly what I want. And given it's just form and fit, not actual function, you're actually able to get that part in hand in a matter of minutes to hours. And so from there, I know I've seen a lot of different fastener manufacturing facilities and a lot of roller bearings, a lot of guide tools to help the wire spools enter the machine. And so a lot of times I hear that those machines, given some of them were built many, many years ago, maybe those companies are no longer in business, maybe those parts are not readily available. A lot of times you are able to design and reverse engineer those parts that were on your machine. And so heaven forbid one of them breaks and you get a line down situation, you don't have to wait for your machine shop to receive those designs, tie up a man on the CNC or on the mill and have those parts created, or even worse, wait on lead times from a shop outsourced. And it's one of those things where you never want a line down situation, but it's always best to prepare for one, especially if you're running with older equipment like this. And so that also ties into the sorting fixtures that I've seen a lot of people, they do, I guess, kind of their own setups when it comes to the output of these machines. And instead of going with the standard, say they came with a bucket that would fill up with like a 50-gallon drum, say that they have special carts that they would like to use, printing out fixtures like this, they could, I guess, angle and point the output of these machines so that they could adapt them to their facility's requirements, whether that be restrictions on space, restrictions on, I guess, shipping, anything like that. And then
yeah, that's really around like the output of a fastener manufacturing system, right? Where you can sort the fasteners coming out of that system, or even from a packaging point of view, you can use additive to help design and build fixturing and tooling to aid in the packaging of a fastener manufacturing facility.
Exactly. So those cold forging and those cold rolling machines, they have an extremely high paced output. And so making sure that your sorting at the end of the day is proper and where you need it to be is super, super important. And then one last point on here that I actually recently worked on were some custom washers. So since these particular pieces of hardware aren't necessarily in tension, and if you're looking for custom washers, you would actually be able to 3D print a good amount of them. So for instance, on the composite machine right here, we had a customer needing specific, these custom designed washers that they had that were interacting with the circuit board, and they needed to be ESD safe. And so they weren't able to find exactly what they wanted. So they were able to find ESD safe material for their Markforged X7. And they were actually able to start printing just small runs of these fasteners. Given they were a low production shop, they were able to print all the ESD safe washers to help secure their circuitry for that one particular project. So this is something like seen on that spring assembly there. That's not the particular project I'm talking about, but it's one of those things where if you need something very specific, like in the washer section, designing and printing them is super, super simple and extremely fast. I think I saw them print, I think it was 300 washers over the course of, I don't know, I think it was 6 hours, something like that. And so,
yeah, I mean, that also applies to legacy parts, right? If somebody is struggling with keeping legacy parts in inventory or having a pile of legacy parts, additive fits well for being able to offer legacy parts, but not actually having to hold physical inventory, right? You can keep a digital inventory of your legacy parts, and if you need one or a client needs one, you can just print that part instead of actually holding the inventory. It works great for custom washers and components around the fastener.
mm-hmm. Yeah, like I said, no nuts and bolts for practical use. And so when it comes to the end users, when it comes to the people that are actually using these fasteners, not the ones manufacturing them, there are hundreds of different use cases on a manufacturing floor for implementing additive manufacturing and helping that speed up your manufacturing process and just make it a whole lot easier. A lot of people, the most common parts that we see is tools, jigs, and fixtures. So it's those custom tools that people were traditionally outsourcing, traditionally sending to some other job shop to have them produce these tools. They were actually able to bring those all in-house. And so instead of realizing like, oh no, this bracket over here had snapped on this machine, and now we have a line down situation, instead of calling up their job shop and saying, hey, listen, we need this bracket here. We need it as soon as possible. And they get back to them with 1 to 2 weeks, which would be pretty good for a lot of job shops. They're able to turn straight to their printer, have it printed out in 6 hours, And that's a whole lot of revenue that they are able to recover from having one of these on site in their facility. And so custom workstations flows into a very similar thing. We see a lot of welding fixtures, and that ties into both composite and metal 3D printing. Between grounding, I guess you would say, components for welding, we can print out those components in copper. And then when it comes to the composite side of things, you can print different fixtures like the one you see down here in Onyx FR, which is a flame retardant onyx. Very strong material for working in high temperature environments like welding. Same thing with guide brackets, whether we're talking hole patterns, looking at adhesive strip alignments, or even body panel gaps for automotive.
Yeah, it's a great tool to help build fixturing around holding components while fasteners are applied to those components. It's straightforward to produce, shape fitting parts with additive, and like on the bottom picture, specific angles, the way things that go together. That way you can hold the pieces and parts and components as fasteners are applied, to keep the final assembly in the shape that you want it to be in.
Exactly. And like I was saying before, if you wanted to mitigate, well, I guess previously, if you wanted to mitigate having a line down situation, you knew there was a specific wear part, you'd be able to stock a whole bunch of them. But at the same time, then you have parts that you're sitting on hand that you're not quite sure when you're going to use them. They're kind of just sitting there collecting dust. And so with this, you get a massive SKU and inventory consolidation where you would just need to store the material and print as you need and house them in the digital forge.
Perfect.
And so going forward with kind of what we were talking about before, this is kind of a couple applications that we have seen in person of fasteners working together with additive manufacturing to provide better solutions than we're seeing before. This is two examples of welding fixtures and assembly fixtures where, as you can see, multiple fasteners used, multiple brackets used. And I think the biggest and best part that I have seen with the people that I've worked with and the other engineers is the fact that when a design change is made, you don't have to go and change all your tooling. You don't have to scrap all your inventory. Since people are printing as they need, they're able to go back and just digitally change their file and send it straight to the printer. And they have it in a matter of hours where they won't have to pay for the tooling costs if they're using a die. They won't have to scrap the inventory that they had already made up. Say that they needed for this fixture on the left here. Say that they realized that angle was a little bit too shallow and they need to make it a little more steep. Instead of scrapping any fixtures that they had before, they would just be able to go into their CAD software, change that angle just a little bit, send it off to the printer, and they'd have it in a matter of hours. It really helps people streamline, and I feel like it's very helpful in engineers thinking outside of the box. People are a lot less pigeonholed into saying, well, this is what we have to make it work. At the end of the day, if you have a 3D printer or any type of additive manufacturing equipment, you have one set area where you can do exactly what you please. You have very limited constraints, and you're able to go about